Here we'll be learning about cells. The definition of a cell is that it is an electrical device used to power electrical circuits by providing a potential difference. And this is the circuit symbol of a cell. It is represented by two lines. The longer side is known as the anode, which is the positive terminal, and the shorter side is known as the cathode, which is the negative terminal. And if we mark the voltages at the positive terminal as VA and the cathode as VC, VA is always greater than VC. Generally, if we take a cell, let's say the EMF of this cell is E, and if it is not an ideal cell, each of these cells, they have specific resistance inside them. If this is the cell, R is the internal resistance of the cell. Resistance of the cell, and E is the electromotive force of the cell. Now we have to learn what a battery is. What is a battery? A battery is a combination of cells, and cells can be combined in two ways to form batteries. The first way is to connect them in series. The second way is to connect them in parallel. Now let's learn about cell combinations. Under this, we have cells connected in series. So let's say we have three cells. This is the first cell, that is the EMF value is E1, and the resistance, internal resistance is R1. Next we have another battery with EMF value E2 and the resistance is R2. And we have another battery that is the EMF value is E3 and the internal resistance is R3. So if we replace all these batteries using a single battery, let's say the EMF value is E and the internal resistance of that battery is simple R. So here in this case, we can say that E is equal to E1 plus E2 plus E3, and R is equal to, since these three resistors are in series to each other, we can say that R is equal to R1 plus R2 plus R3. Here note that the cathode is connected to the anode in each case. Here in case 2, note that the terminals of this E2 cell is inversed. Now, if we take the resultant EMF value, it will be E1 minus E2 plus E3. Since it is opposite to the connection of the other two cells, the EMF value will be subtracted. But it won't change the value of simple R. Simple R will be R1 plus R2 plus R3. Now, let's talk about parallel connection of cells. Here I have taken the first case where all these three cells of EMF value E1, E2 and E3, they are connected with the same cathode and the same anode, and each of them have an internal resistance of R1, R2 and R3 respectively. So if we represent this system using a single cell of EMF value E and internal resistance R, we can say that E over R is equal to E1 over R1 plus E2 over R1 R2 and plus E3 over R3. And also, since these three resistors are in parallel to each other, 1 over R1 is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Here note that in the second case, the terminals of this E2 cell is interchanged. So when we take the equivalent resistance, it won't be a different one, it will be the same one. But if we take the electromotive force or the EMF one, we will get a negative sign because it is in the opposite direction when compared to E1 and E3. Next, we have to learn the potential difference across the two terminals of a cell. Under this, we have the first case where the current flows from the cell, and the second case, the current flows into the cell, and in third case, current does not flow in or out of the cell. And let's take the first case, case 1. Here I'll be drawing the diagram of the cell, and it has an internal resistance as well. Let's say the internal resistance is E, and the electromotive force is, the internal resistance is R, and the electromotive force is E. We have to find VA minus VB. And in this case, the current flows from the cell, so I will be moving out of the cell. Here, if we take VA minus VB, we will get E minus I times R. And in the second case, the current flows into the cell. So, if we redraw the diagram of the same cell, but in this case, the direction of the current is opposite. So here, if this is VA, this is VB, VA minus VB is given by E plus IR. So in this case, it is minus, and in this case, it is plus. In the final case, that is the third case, there is no current flow. So I is equal to 0. Let's draw the battery again. So this is VA, this is VB. And the electromotive force is E, and the internal resistance is R. So here, since I is equal to 0, VA minus VB, let's say it is, let's take this equation. So I is 0, then this entire term will be 0. So VA minus VB will be E. So these are the three cases. If the current is flowing out of the circuit or out of the cell, it should be E minus IR. If the current flows into the circuit or the cell, it should be E plus IR. If there is no current flow in or out of the cell, the difference between the potentials of the terminals of the cell will be equal to the electromotive force of the cell. Now also note that if the cell is ideal, there is no internal resistance, that is R is equal to 0. Therefore, in that case also, it will be VA minus VB will be equal to E, because if there is no resistance, if R is equal to 0, and now let's say V is the difference in potential between the two terminals of the cell. In this case also, this IR product will be 0. Therefore, if the cell is ideal, the difference of potential between the two terminals will be equal to the EMF of the cell. Now let's move on to a question. Here, the electromotive force of a cell is 1.5 watts. When the cell is short-circuited, a current of 3 amperes flows through it. Roman number 1, we have to find the internal resistance of the cell. Now, here the cell is short-circuited. Or let's say this is the internal resistance. Let's say it is R. And they have given the EMF value. It is 1.5. So if this is the cell, they have short-circuited it. So should connect the positive terminal and the negative terminal using a wire. Here there is a current flow because we have a resistance. So let's mark the current I. And the current is equal to 3 amperes. Now let's apply V equals IR to this circuit. V is equal to 1.5 and the current will be R and resistance is, let's say, R. The current is 3 amperes. So R will be 1.5 divided by 3, that is 0.5 volts. This is the Roman number 1. And in Roman number 2, find the potential difference across the terminals of the above cell when resistor of 2.5 ohms is connected to its end. Let's draw a simple diagram. This is the external resistor with resistance 2.5 ohms and the EMF value is 1.5 and the internal resistance will be 0.5 ohms. And we have to find the terminals potential difference. So here in this case the current will flow out of the battery. So we have to find the potential difference across the terminal. So it should be V is equal to E minus IR, right? So E we know 1.5, I we don't know, but the internal resistance is 0.5. I have found it in the first Roman number. So we have to find the current flow. Here, if you take this cell, the resistor, this is the potential difference we have to find, and I is the current through this circuit as well. So, if you apply V equals IR, V to the resistor, the 2.5 ohm one, I we don't know, but R we know it is 2.5. So if we subject I, we get V over 2.5. It is the second equation and this is the first equation. So here we can substitute the second equation in the first equation. Therefore we get V equals 1.5 minus V over 2.5 times 0.5. So we get 1.5 over V over 5. So if we simplify this, we get 6V over 5 is equal to 1.5 can be written as 3 over 2. Therefore, V is equal to 3 over 2 times 5 over 6. So if we simplify this, we get 5 over 4 watts, that is 1.25 watts. Now let's try another question. If n number of identical cells of EMF value E0 and internal resistance R0 are connected in series and parallel, find equivalent resistance and equivalent electromotive force. Let's consider the series case first. So we have n number of cells, n number of identical cells. So this is this is E0, and the resistance is R. So this pattern continues until n. So here the equivalent electromotive force, let's say it is EEQ. So that will be E0 times n. And since these resistors they are in parallel to each other, they are in series to each other, you can say that Req is equal to R times n. If we consider the parallel case, we have n number of identical cells. The internal resistance is R0. It's corrected here also. It is R0. And the electromotive force is also E0. So here, if you take the equivalent resistance, it will be 1 over Re times 1 over R0 times N. So this pattern continues. So Req will be R0 divided by N. And we have to find EEQ. So EEQ is equal to Req times E0 over R0 plus E0 over R0, and this pattern continues until for n number of terms. Okay. So this will be EEQ divided by Req, and this will be n times E0 over R0. So instead of Req, we can write this equation. So we get EEQ is equal to R0 divided by n is equal to n times E0 over R0. Therefore, EEQ is equal to E0. So here we can say that even if you connect n number of identical cells in parallel, the equivalent EMF value will be equal to the EMF of a single cell. Okay, now let's move on to another question. When two identical cells are connected in series and a resistor is connected across the ends, a current of 1 ampere flows through the circuit. Later, when two cells are connected in parallel and the same resistor is connected across the ends, the current through the resistor is 0.6 ampere. If the EMF of the cell is 1.5, find the internal resistance. In this case also, let's consider the series case first. So we have two cells, both of them are identical, and these are the internal resistance. These are the two cells. We have the external resistor, which is, let's say it is R, and the current flow is 1 ampere. So here, instead of this two resistors, two cells, we can represent using a single cell. The external resistance is R and the internal resistance is, you have two resistors, so that will be 2R. You have two cells, that will be 2E. and the current will be 1 ampere. So by applying V equals IR to the circuit, we can get 2E is equal to 1 ampere times R plus 2R. So 2E will be R plus 2R. It is first equation. And also they have given that the EMF value is 1.5 V. So let's substitute it here. So we get the equation capital R plus 2 simple r will be equal to 3. Now let's consider the parallel case. We have the two cells. We have the external circuit, external resistor, let's say it is R. Here we can simplify this cell, these two cells into a single cell. This will, since these two are resistors are in parallel, it will be RO2, and the equivalent resistance of, the equivalent EMF value of these two cells will be E, because they have the same magnitude, and previously we proved that, right? And this will be R. The resistance, the current will be 0.6 ampere. Then by V equals IR, we can say that E plus E is equal to 0.6 times R over 2 plus R. They have given the value that E is equal to 1.5. So we can simplify this. 1.5 can be written as 3 over 2, and 0.6 can be written as 6 over 10. So if we simplify 3 and 3 will get cancelled off. Here it will be 5. So 5 over 2 is equal to R over 2 plus capital R. Then if you simplify this, we get 2 capital R plus simple R will be equal to 5. That is the second equation. So in this case, we have to find the internal resistance, that is R. So we have to find simple R. Then by the first equation, we can subtract capital R, that is capital R is equal to 3 minus 2R. Then we have the second equation. We can substitute this value. Then we get 6 minus 4R plus R is equal to 5. So 1 is equal to 3R, 3 simple R. Therefore R is equal to 1 over 3 ohms.